Right, 10 o'clock. As said, we'll start sharp at 10. So welcome everybody. We've got a very big crowd and a very international crowd. So welcome everybody. As you can see, you are muted on entry and this webinar is being recorded. If you have any questions, please put them in the Q&A section and either I'll address them verbally during the session or afterwards in the Q&A time we have left, if any. Otherwise, I'll try and do my best to address them after the session and contact you by email or whatever means possible. So enjoy. And like I said, if you have any questions, feel free to ask them in the Q&A. What we are going to talk about is the developments and trends that are currently going on in Wi-Fi, as well as a couple of standards that are already published and active, but we'll try and see how adoption of those standards are being done at the moment. So let's start off with a little introduction, so at least you'll know who's talking to you. Then we'll go through the history a little bit, because you've seen this stuff probably hundreds of times, so I'm not going to spend too much time on that. But we'll look at what's happening now in the standardization, as well as some fun and upcoming standards and developments that are a bit out of the ordinary, or a bit new, a bit fun, and we'll see what happens with them through the time to come. A bit of adoption as well, things like WPA3, I was going with the adoption of that, and some innovative stuff that I found very interesting and want to tell you about what I've been seeing online and in other publications. So first of all, short introduction. This is me. I'm a technical consultant wireless at Consia in the Netherlands. Been there for over 25 years, and I've been doing Wi-Fi or wireless back in the days, I was what's called, since 1998. So I've seen a couple of things, done a couple of things. You see a few examples over there. I'm a CWNE number 325, and if you don't know what it is, please visit cwnp.com, which is a certification, a new vendor neutral certification, going from a very entry level up to the highest level, which is this expert level. Besides that, I am real fond of the outdoors, love to go hiking. I'm also an amateur astro geek and photographer, and do a bit of drawing every now and then. So that's me. Let's not wait too long for the rest of the content, because I want to share some stuff that I've seen around Wi-Fi that I want to share with you. Starting with when it all started. Now, I'm not going to go through each and every one of these bullets, because there's lots that have been happening since 1997, the birth of .11. Well, actually, the birth of the technology is way before that, and there's the link to my astro geekness. It was actually part of a astronomy development that led to the birth of Wi-Fi. We're now in 2022. And a lot has happened in the meantime, but we're going to go for the 2021-2022 part, what is happening now and what is coming up in the short term. But this is just a fun overview to see where it all started and what has been happening in the meantime. So at the moment, these are the published IEEE standards. First of all, the roll-up in 2020, which is like the consolidation of a lot of standards into one big standard, just to make it a bit easier as an overview, but still all those different standards, all those different acronyms and letters are in there. And one of the most common one at the moment is, of course, 11AX. So that's the Wi-Fi 6, as they call it nowadays. Standard that's been ratified in 2021. There's also been a ratification of the 60 gigahertz standard. You're not going to see that in enterprises, at least I have never seen it there. It's mostly used for in-house entertainment systems and stuff like that. But it's been ratified as a .11 standard, as well as a wake-up radio standard that's been ratified last October. Haven't seen anything from that either, but this is just to give you an idea of what is happening in the IEEE domain. What we are going to talk about is, well, not all of these, but a couple of these, because these are the most current task groups at the moment that's being worked on by the IEEE. And it's either a new standard or a refinement of a couple of standards, and we're not going to dive into all of them, but I will focus on a few that already hit the news or you may have heard of or I find very interesting, or you might as well be asked about when talking to customers or with other people in your working environment. So what are we going to focus on? Well, first of all, the next positioning, next gen positioning, shortly the 11AZ standard, as well as the 11BB standard. We're going to look at a little bit at extremely high throughput, so that's the 11BE standard, as well as WLAN sensing. Now, I'm not going to touch on the other ones, but I want to give you a short idea of what they encompass. For instance, the 11BC, it stands for Enhanced Broadcast Standard. Imagine that you have like a broadcast system. Typically in Wi-Fi, every packet needs to be acknowledged. And if you want to broadcast something to a large group, say for instance, video or whatever, there have been some proprietary solutions from different vendors, but this is the first time that there's actually going to be a standard that addresses this issue. So that's the enhanced broadcast. Next gen vehicle to everything communication, so that's 11BD is exactly what it means. Vehicle to everything, vehicle to vehicle communication. There are a lot of 11 or .11 standards in inter-vehicle and intra-vehicle communication that we usually don't get involved in. But it's just to give you an idea that also the .11 standard is involved in there as well. And this is the next generation standard that they're working on. As for the 11BH and BI, first one, BH is MAC randomization that every client vendor like Apple and Samsung and all those have been implementing, but they pose challenges for the networks. For instance, if you have like a loyalty program that's based on MAC address recognition and all that stuff, privacy, location sharing and all those things, those are addressed in these two standards, 11BH and 11BI. So just to give you a short overview of what we're not going to talk about, but anyway. So let's start off with the first one that we are going to focus on, which is 11AZ. This is called the next generation positioning system, which is based on something that's already there, which is called the Fine Time Measurement Protocol. It also builds on the 11AX protocol, so that's Wi-Fi 6, and it uses the packets that are in there for beamforming, which are called null data packets, to try and communicate time differences. So the main part in this is there are several systems that use timing for location purposes. One of the most common ones is time difference of arrival, so TDOA. And the big difference here is with TDOA, it actually uses the real time that needs to be synchronized over the different devices in order to see a difference, which makes it very difficult because in Wi-Fi or any other radio communication system, the data travels at the speed of light, which means that if I have a difference in time of 1 nanosecond, that means that my location can shift 30 centimeters. Now, 1 nanosecond synchronization requires very accurate chipsets and crystals, so that makes it difficult to actually make this work. That's why the time of departure, time of arrival system, so TOD and TOA, is used to determine the difference in time without synchronizing clocks. So basically, it makes use of relative timing with no accurate time synchronization because it uses the time that it sends something, the time that it sees it, that packet coming back, and the difference between those is what's called time of flight. Now, if you multiply the time of flight by the speed of light, since electromagnetic energy is transmitted at the speed of light, that gives you a distance. So that's the way the 11AZ is supposed to be working. Again, it's a standard in development. I haven't seen anything from it yet. It also depends on whether manufacturers like infrastructure devices as well as client device manufacturers will implement this standard. Once that's done, you can make use of this standard. And then again, of course, it has to do with other applications that make use of these location solutions to make a complete ecosystem. But just to give you a heads up, this is what's happening in the background. If you compare this with other location standards that are popular at the moment, which is ultra wideband and primarily Bluetooth, next to the RSSI solutions that are already there in Wi-Fi, you see that the 11AZ kind of sits in between ultra wideband and Bluetooth with regards to distance. So the accuracy is expected to be somewhere between 1 and 3 meters. But especially the reliability makes use of Wi-Fi. So it has a nearly a line of sight solution, which is a bit better than Bluetooth. Again, it sits in between there. It can be used up to 50 meters or 100 meters, which is typically what's been called the nominal distance within Wi-Fi systems. In reality, it's a lot closer because of density walls and all that stuff. Plus the fact that the data rate is a lot higher because you're using Wi-Fi, which is typically a higher data rate than any other system used for location or low bandwidth communication like Bluetooth. So again, it sits a bit in the middle there. So it depends on your use cases. If you want something accurately located within 10 centimeters, either Bluetooth or Wi-Fi is not going to help you. But generally, the most use cases don't require anything better than 5 to 10 meters, to be honest. So if you can get into the 1 to 3 meters accuracy without any special antennas and deployment scenarios and all that stuff, that would be a great benefit. But we'll see what happens. Next one, 11BB. Again, this is something that's been around for quite a while. Not in a real deployment scenario. I still want to have my hands on some of this stuff, but it's being developed at the moment, which is called Li-Fi or light communication. This actually has been developed back in 2011, so we're well over 10 years ago when this was presented, and it is developed and invented by a guy named Harald Haas, which is a German professor. He did a TED talk on this back in 2011. If you Google it, if you Google Li-Fi Harald Haas, you'll get the video, but you'll see that. Give it a try if you want to. Basically, what it means is communicating over light. Now, again, like I mentioned before, with the accurate location solutions, so the 11AZ solution, Wi-Fi signals or any data signal using the electromagnetic spectrum basically sits within the spectrum of light. So light is electromagnetic energy as well as Wi-Fi signals are electromagnetic energy. The only difference is our eyes are only capable of seeing a certain amount of frequency within that spectrum, and we call that visible light. Now, for Li-Fi, oh, and by the way, Li-Fi doesn't mean anything just as well as Wi-Fi doesn't mean anything. For those of you who don't know or always thought that Wi-Fi was wireless fidelity, it's not. It's just an acronym that was conjured up for marketing purposes, because apparently they didn't think that 11 or 802.11 kind of sounded really cool. So Wi-Fi is something that just was thought up, and it kind of stuck in there, and we still call it Wi-Fi. So Li-Fi isn't light fidelity. It's just an acronym on Wi-Fi. We actually have to call it light communication, so LC, but that's just something on the side. Anyway, it's one of the first and only standards that's actually being mentioned in the 5G 3GPP standard revision 15 as an option for endpoint connectivity. Now that means that the 5G, 4G consortium, which is the 3GPP, actually addresses this as one of the access technologies. So that could mean that customers are going to talk about this. You're going to talk about it. You're going to be faced with it. So getting a standard to actually support this would be very nice. Depends on whether companies are going to develop hardware around this and which companies that are going to develop this actually, because clients need to support this as well. Because you have to have something that decodes the light, but you also have to have something that transmits the light in such a way that you can integrate data in it. Now, there's a lot of spectrum in there because we are using light. But typically, the standard now says, well, you have to get into the 800 to 1,000 nanometers with regards to the standard, which is the infrared, because, and that's the main reason, safety reason. It is invisible to humans. Apparently, they don't care about animals, but anyway, for us as one of the prime users, of course, getting invisible light that's unharmful to your eyes is, of course, a very important factor. So that's the reason why they went for that spectrum. The standard dictates that you have to have at least a minimum data rate of 10 megabits per second. Now, that's not very interesting. However, at least one mode should support 5 gigabits per second. Well, it uses different channel access methods like HCF. It uses overlapping base station services. And it also needs to encompass a standard to transition between the light communication physical layer as well as the traditional 802.11 Wi-Fi physical layers, in order to make it easier for the end user to roam between the traditional quote unquote Wi-Fi solutions and the light physical layer. That's going to be a challenge because that's roaming on a whole different level. And the challenge is going to be, well, besides the fact that we have like 10,000 times more spectrum than Wi-Fi, since we've got this whole range of frequencies that we can choose from, not taking into account that we're going to focus on the infrared part. But anyway, it also is secure because it needs line of sight. In other words, if you don't come within the bundle of light that actually houses the data, you're not going to receive anything. That can also be seen as a downside because you need line of sight directly in order to receive data, but it can also be seen as a security measure. The other benefit is it doesn't have any interference of neighboring networks because, well, it's light, right? However, some tests have shown that sunlight or light passing through certain materials and even ordinary lighting can interfere. Depends on how much and how well it can be adapted to. But again, any benefit could also be seen as a problem. One of the other things is it might have quite a higher installation cost because you have to have lighting systems that support this. On the other end, we're starting to see more of the LED systems within offices that can also do more than just give light. There are sensors in there. There's probably, or maybe even the future communication systems in there. And I know from at least one of the vendors, which is Signify, previously known as Philips, that's already looking into this in their lighting armatures. Besides sensoring and all that stuff, also put in something like light communication systems. So it's just something that I've noticed as a standard in IEEE, which usually means that it doesn't take that long before the first equipment comes and hits the market. So next one, focus on 11BE. Well, there we go. It's Wi-Fi 7. And we just got used to the fact that we needed to call things Wi-Fi 4, 5, and even 6. And now they're already talking about Wi-Fi 7. And there's the 6E in the middle there. And we're going to talk about that a little later. But Wi-Fi 7 is already on the drawing board for quite some time. And it's expected to be released in a first phase at the end of 2023. So that's by the end of next year. It's going to be a tough day to target for, but again, it's going to be in multiple phases, basically like we've seen with 11AC, so Wi-Fi 5 nowadays, which came in 2 phases as well. It's not really clear what's going to be in phase 1, what's going to be in phase 2, and even if the end of 2023 is feasible, because we've seen quite often that IEEE timelines tend to shift because of all kinds of challenges, and well, you never know what's going to happen in the world, so that's playing a role as well. But at least these are the first target dates that they've released. It's being called EHT, so extremely high throughput. Makes you think what the next standard needs to be called, but anyway, we'll see. And some of the features are really wide channels, this has also some impact on whether or not you can use the full spectrum, especially in 6 gigahertz, which I'll come to in a moment. But one of the interesting things that specifically target, again, bandwidth, because that's always one of the prime targets within new standards, is what's called MLO, so multi-link operation. And what it basically means is when you connect to a Wi-Fi network now, you either connect to 2.4, God forbid, 5 gigahertz or 6 gigahertz at the moment. And it's either one of those. It's not and one of those. It's always one of those. The multi-link operation allows you to set up I'll call it an ether channel, so a link aggregation between, for instance, 5 and 6 gigahertz. Bundling those two frequencies together, if you can call it that, to create a multi-link and get really high data rates. Depends on your use case, of course. If you're going to need this or not, I always say you don't need 5 gigabits per second to send out an email. But anyway, it is something that's being developed at the moment. Besides really high bit rates with 4096 QAM, coordinated multi-user MIMO, which is something that's basically back to one of the first standards that they tried. So let me rephrase that. Back in the days when wireless was being developed, they looked at two different methods. One was letting the access point coordinate all the communication that clients can do, or make it something that clients and access points figure out together. So what happened was the latter solution became the de facto solution, which means that it's called DCF, so distributed coordination function, basically telling the access point and client to take on a fight together, and whoever wins gets to send some data over the wireless channel. If you're going to look at coordinated multi-user MIMO, basically what you're saying here is let the access point determine who's going to transmit or not. So it's kind of a mix of both solutions, where in the beginning, DCF was the one that actually made it. Well, we'll see what happens. So I've been looking around for some news on Wi-Fi 7, and one thing that I found interesting was the latest and greatest chipset from Qualcomm, which is a tri-band chip. So it's 2.4, 5, and 6 gigahertz. It can support those 4096 QAM constellations, and does this high band simultaneous link and multi-link solution. So either transmit both on 5 and 6 gigahertz in parallel, or aggregate it into one big link, getting you up to a 5 to 6 gigabits per second throughput connection, if possible. We'll see, but you'll need really wide channels to do that. And it's kind of set in the specifications that I found that it's going to support Wi-Fi location, but they weren't addressing it as 802.11az. I'm suspecting that that is AZ, but I couldn't find anything about it. But at least one of the vendors, one of the largest vendors of Wi-Fi chips, Qualcomm in this case, is already developing a Wi-Fi 7 chipset. That doesn't mean that clients are going to pop up within a couple of months with this new chip, but it is there already. And just to give you a little insight, there are a lot of companies working on the background that take quite a lot of time to test these chips, to build radio systems around them, to actually make a product. So these kind of vendors need to be upfront in the technology war, and this is one of the things that I found about it. So next is a focus on 11BF, which is something that I found really interesting, and it's called WLAN sensing. I've seen some videos on that with the first developments, and it's now being poured into a standard. It operates in both the lower, quote unquote, and higher frequencies, so 1 to 7 gigahertz, as well as in the 60 gigahertz frequency range. Although the last one, 60 gigahertz, kind of shortens your range dramatically. And typically because 60 gigahertz is the same frequency, or around the same frequency, that starts to vibrate oxygen molecules in the air. So that's going to absorb a lot of energy, limiting your distance dramatically. So the point of WLAN sensing in 60 gigahertz kind of diminishes, I think, but we'll see. Anyway, it is being taken into consideration into the standard. And one of the things that makes this interesting is that it doesn't require a line of sight. So it actually can see through walls. Of course, this depends on the type of wall, because some signal has to penetrate the wall, but it makes it possible that by the change in signals and the direction of signals and the intensity of signals to actually detect a person or a chair or somebody falling, or heat or whatever movement, as long as it changes the characteristics of the RF, it can actually see it, and it can see it quite accurately to a point where even hand gestures and respiration monitoring, so how often does someone breathe in, breathe out, even those little changes in movement can be detected if you're starting to look at the millimeter wave sensing. So in order to go into the 45, 60 gigahertz discussion with regards to the distance, it might as well be possible that, for instance, hand gesture systems and monitoring for medical solutions are going to start this frequency for sensing systems, because there the distance is a lot shorter, and you won't be needing this for detection of falling or if somebody is present in a room during a fire or whatever. So there might be a use case for those higher frequencies, but again, it limits your distance dramatically. So it all depends. But like this picture shows, it could well be that we're going to start seeing these holographic screens that you can operate by just simply making hand gestures in the air, and to have a contact-free control, which nowadays, with all the trouble going around in the world, might as well be a very good idea. It's just an insight. I find it very interesting. Let's see what happens. So these were the standards that I was wanted to focus on for now. We're going to dive into a little bit of adoption, because all these standards are really good and really fun, but it all comes down to how is the adoption of all these standards that are being developed. And one of them that I don't see that often, but is going to be used a lot more now, within a couple of months or years, is WPA3. It is the highest Wi-Fi security standard at the moment. We had a couple of bumps to go through with regards to Wi-Fi security. Back in the days when it all started, wired equivalent privacy, excuse me, was the first one. Well, we all know how secure that was. But anyway, then things like WPA and WPA2 came around. And since WPA2, not a lot has happened on Wi-Fi security within Wi-Fi itself. So I'm not talking about 802.1x, which is, of course, the best way to secure your Wi-Fi. It's the encryption and key exchange in general that's being used by Wi-Fi. So there was this period of around 13 years where nothing really happened with regards to WPA2. Then came the crack. So somebody was able to show the vulnerabilities in WPA2, showing that, again, Wi-Fi was insecure and all that stuff. Well, basically, you need really good tools to crack WPA2. But again, there was a flaw in there. So up came WPA3. And since then, I haven't seen very much deployments of WPA3, in my opinion, for one good reason, and that it's not a requirement. So Wi-Fi 6, 11AX, does not require you to use or support WPA3. In other words, you can easily deploy a Wi-Fi 6 network on WPA2. And since most of your clients are supporting WPA2 since, well, a lot of years, that's the easiest way to upgrade to a Wi-Fi 6 network. Whereas if you want to go to WPA3, you need to upgrade your drivers, operating system, and so on. You need to test this and all. So the step to actually make towards WPA3 isn't all that difficult, but it encompasses more work than just using WPA2 that everybody is supporting anyway. However, when you go into Wi-Fi 6 6E, so the extension of Wi-Fi 6, mostly known for its 6 gigahertz support, you are required to support WPA3. Even better, you're not allowed to use WPA2. This also poses a challenge because that means that if you're going into a Wi-Fi 6 WPA3 network and you need to roam to a 5 gigahertz network, say Wi-Fi 6 network, you would probably be best off to use WPA3 there as well. So we'll have to see how to work around that because the first Wi-Fi 6E access points are hitting the market as we speak. So that all takes a bit of testing and figuring out how we're going to do this. But just keep in mind that when you're going into Wi-Fi 6E, there's no WPA2 there. You're going to have WPA3. And that's my hope for a far more faster push of a higher security level than we are using at the moment. As for the adoption of Wi-Fi 6, known as 11AX, already announced back in 2018, and it was started from a development standpoint 4 years earlier, and that's what I mentioned with Wi-Fi 7 and all the other standards. There's a lot of time being put into developing the standards. It does take a lot of time. So it took 4 years to create this 11AX standard, where after that the certification start. And the first ones for 11AX started in 2019 and were fully approved in 2020 and published in 2021. So here you see some of the timelines that are that you need to take into consideration when these new standards are being developed. Anyway, what we see now is basically every new Wi-Fi network that's being installed, either for a completely new development installation or a lifecycle refresh, you'll probably go with Wi-Fi 6. That's the most obvious way forward. You could go with Wi-Fi 6E, of course, but you have to keep in mind that the first products are now hitting the market. The really high-end access points, and they're starting to get more access points available now, but the clients as well need to be supportive for 6 gigahertz. For 5 gigahertz Wi-Fi 6, and sorry for the confusion, but that's the way they call it nowadays, there's a lot of support now. So you've got a lot of Apple MacBooks and Apple iPhones that support it, the Asus, Dell, HP, Lenovo laptops, a bit more higher end, but not even the highest ones are supporting Wi-Fi 6 now. Most of them can, especially laptops, can be fitted with a chipset anyway. Smartphones are being fitted with Wi-Fi 6 clients. So that's really an extensive list, and I'm just showing a part of that list on this slide. But that's really being adopted quite fast now. It depends on the situation where you find yourself in. So in the hospitals, you generally see a lot of medical equipment that takes a lot of years either to be replaced or be fitted with the newest technology. If you're in a educational environment, you're going to see a lot more Wi-Fi 6 clients. So again, it all depends on what your requirements are and what kind of vertical you're in. But this is basically what we see. Then Wi-Fi 6E, I mentioned it already. The E stands for extended. So it's an extension of Wi-Fi 6, and it kind of makes it a bit of well, a false statement, in my opinion, because it's not extending Wi-Fi 6 in any way other than it is 11AX, and that's it. So Wi-Fi 6 is 11AX, Wi-Fi 6E is 11AX. So also, the only extension is into the 6 gigahertz frequency band. But then it's not really an extension, because that would suggest that you can move around freely between 5 and 6 gigahertz, which is not the case. Either you connect to a 6 gigahertz frequency, or you connect to a Wi-Fi 6 5 gigahertz frequency. Oh man, all these numbers. Anyway, almost any vendor, if not every vendor, has an AP available at the moment, or has announced an AP that's going to support 6 gigahertz. And this is going to be the push to WPA3. Again, it's 11AX only, but it only supports WPA3 and not PA2. And it also does not support open networks. So your general guest network where you just have to access the Wi-Fi without encryption, get hit by a portal, God forbid, and accept some funky user requirements, and that's it. No, it's not going to be there. You have to have something that's called OWE, which is basically the equivalent of an open network, but then in the secure WPA3 network. So it's 6 gigahertz spectrum. The first approval was 2 years ago, 2020 in the US, so FCC regulatory domain, and they've got the full 1200 megahertz of spectrum. Lucky them. We're here in the ETSI domain, and we've been granted a little bit less than 500 megahertz of the spectrum. And that being said, it's also the first 500 megahertz of this entire 1200 megahertz spectrum. So it is a lot more spectrum. It's more than we have in any other band. It's completely clean. So there are no interferers in there that we need to take into consideration, such as radar and all that stuff. It will give you gigabit speeds if you have the requirement for that. You can also adopt wider channels. So something that we've been able to do in 5 gigahertz, but because of the limitations with radar detection and all other stuff, we usually don't go beyond 40 megahertz in 5 gigahertz networks. As for the 6 gigahertz networks, that's a completely clean band. So the chances are that you're going to see 40 megahertz as a standard and 80 megahertz as something that's, well, easily to be deployed, easier than you would in any 5 gigahertz network. As for the 160 megahertz wider channels that you are able to use in ETSI, probably not so much unless you have a really specific use case. The reason for doing that or not doing an 160 megahertz channel is what you see here at the bottom of the slide. There you see the frequency and radio bands and the channel width. And you see that in our 6 gigahertz domain, so the European 6 gigahertz domain, we can have 3 separate 160 megahertz channels, which gives you the same problem that we always had in 2.4 gigahertz, and that's channel overlap. So either if you have a network that only consists of 3 access points, you're good to go. Probably not, because most networks exist of a lot more access points. So looking at the 80 megahertz channels, now you've got 6 separate 80 megahertz channels. You've got 12 40 megahertz channels separated from each other, and up to 24 in 20 megahertz channels. So you see there's a lot more choice there with regards to 20, 40 or 80 megahertz channels. And again, I don't suspect you're going to see a lot of 160 megahertz channels, but we'll see. So why only 500 megahertz of spectrum? It runs up to 4605 megahertz frequency, and as of 4625 megahertz, the fixed mobile networks start to appear, as well as the higher frequencies which encompass the space to earth and earth to space communications between satellites, and up to and into the 7 gigahertz, where again you have the fixed to mobile system. So that's the reason why they said we're not going to allow anything of Wi-Fi into those domains yet. It's not a fixed decision. As of 2024, they're going to reiterate the standard, or at least the the agreement that they came up on, and see if it is possible to extend this frequency spectrum for Wi-Fi into the higher frequencies. But again, until 2024, this is what we have to deal with, and after that, we'll see what happens. From an adoption standpoint, well, green is good, except if it's light green, because then you're still considering if you're going to allow this or not. But if you look at the Northern Europe region and Europe as a whole, much of the countries have adopted the Wi-Fi 6E spectrum in the first 500 megahertz of band. So this is where we are at the moment. Then the question is always already raised, do I need to redesign? Do I need to redeploy access points in a denser deployment? What's going to happen? So as always, within any technology, it depends. That's the standard answer we're always going to give you. You have to deal with what can your client do? How's the transmit power and the receive sensitivity of your client behaving? What about walls? I mean, if you have concrete walls, I don't care what kind of frequency you're going to use, nothing's going to penetrate that enough to give you a good connection. Distance is a part of the equation as well. So is channels, density that you require with regards to the client. So there's too many factors to give you one simple answer. However, in general, the difference between 5 and 6 gigahertz isn't all that much, especially if you look at the higher channels in 5 gigahertz, and you see that at the bottom right of the slide. If you look at the start of the 6 gigahertz frequency spectrum, it's actually at the end of the 5 gigahertz spectrum. So if you look at the free space path loss, so that's the loss within the first meter going from the access point into the free air. If you look at the 5 gigahertz path loss from the access point in 1 meter, it's 47 dB. If you look at the path loss for 6 gigahertz in 1 meter from the access point, it's 49 dB. So there's a 2 dB difference. Now, if you know that a 3 dB difference means like half the power, that sounds like a lot. But from a Wi-Fi design standpoint, it probably in most cases doesn't require you to do a redesign at first. But again, please look at what are your requirements. Keep in mind that most WLANs have been put in like 5, 6, 7, or even more years ago. In that time, your requirements and your client density and your applications and whatnot will probably have changed dramatically. So take that into account with regards to looking at, do I need to redesign or not? Validating your design is therefore always a best practice. So I always advise that to look at your current installation anyway, if you are going to consider either Wi-Fi 6 or 6E. So if you look at a simulation, and this is an Echo House simulation of a Wi-Fi 6, so an 11AX 5 gigahertz access point, capped off at minus 65 dB, and you take a look at what a simulated 6 gigahertz access point would do, you see that the difference is, well, not that much. So this is just for your reference to give you a little bit of idea of what a Wi-Fi 6 versus a Wi-Fi 6E, so 5 gigahertz, 6 gigahertz, means with regards to the range that the access point can reach at a minus 65 dB signal strength, which is typically what you will use for like voice situations or voice installation and stuff. What I'm not considering here is how well your client can receive this. So keep that in mind. If you have a really bad client with really bad antennas, this minus 65 dB needs to be taken into consideration from the client's perspective. I'm just putting it out there. Keep that in mind. But this is just to give you a little idea of how much this frequency difference actually means in a simulation. Right, so that was a bit of adoption. Now, a few slides and the last few slides on innovation, and I'm gonna look and see if there are some Q&A, is something that I've been seeing every single time, plus a few things that are really interesting. But first off, this one. This is something that's always being mentioned as soon as the 3GPP comes with a new standard. Either it was 3G, it was 4G, and now with 5G. And I'm talking about the cellular acronyms now. So that makes it a lot more confusing now that they're using the same or sort of the same numbering scheme in Wi-Fi. So Wi-Fi 5 is about the same period of time where 4G was there. Now with Wi-Fi 6 and 5G, they kind of supplement each other. So that makes it all a lot confusing. But I'm talking about 5G in the cellular world here. And again, it's being mentioned, well, this is going to kill off Wi-Fi. It's the end of Wi-Fi. Clients are going to use 5G all over and so on. The reality is, each time that a new 3GPP standard came to market, there was an absolute boost in Wi-Fi deployments, either in client adoption, in installations being done in buildings, applications, and so and more. Furthermore, if you look in the 3GPP standard for 5G, it now extensively describes integration with other access technologies, and they put that under the what they call the ATSSS. So that is access, traffic steering, switching, splitting. And what it basically means is you need other access technologies for instance, indoor solutions in order to work with 5G and keep the load at a respectable rate. In other words, getting the 5G signals into buildings with enough density and enough capacity requires very huge installations and very expensive installations. Plus the fact that we see a lot of offloading in the cellular world into the Wi-Fi world, especially now with Wi-Fi calling and all that stuff. So it's one cannot survive without the other. That's basically what I'm saying here. And we've seen that with 3G, we've seen it with 4G, we're seeing it with 5G again. So depending on who you talk to, somebody from the marketing division of 5G developer will probably say that 5G is going to win every single battle that you put out there. The reality is, from a technology and a technical standpoint, you're going to have some other access technology besides that. So the demarcation will probably be indoor versus outdoor, because outdoor Wi-Fi in 6 gigahertz, for instance, 6E, requires some special attention. And to be more specific, it's not there yet, at least not in Europe, because 6 gigahertz legislation requires you to conform to certain restrictions. I was searching for the word there. For instance, you're not allowed to use external antennas that are detachable from an access point. So if you're going to go outside, you also need to keep in consideration what they call incumbent, meaning everything that's already using 6 gigahertz. And up until now, I haven't seen anything in the ETSI domain that's going to make use of that. So keep that in mind with your 6 gigahertz deployment. But if you look at this picture at the bottom, there's going to be like something of an overlap between indoor and outdoor, where 5G business-to-business solutions are more common, and whereas Wi-Fi will be more used for business-to-consumer solutions, basically the same demarcation that you see now with 4G and Wi-Fi. So another thing that I found really fun to read about was wireless power. Now, in the world of IoT, you see a lot of devices that require very little power, but they still need some form of power. There are some devices that can use kinetic power now to actually send out a Wi-Fi signal or a Bluetooth signal. But there's been a university, in this case, the University of Singapore, that's done research by using what they call spin torque oscillators. So electronic oscillators that harvest 2.4 gigahertz signals and convert them in a step-up converter into 3.5 and 4 volt. What that does is it lights up a LED, it powers on a low power or low voltage system, and basically by charging a system for 5 seconds using these frequencies, they can keep this LED burning at a stable and decent voltage, which is very interesting if you look at the IoT domain, where you may not have to have a lot of power and only have to transmit every once in a few hours or something. If you can harvest this energy and store it in a battery and only use it when you have to transmit like a little bit of data, all you need is a battery that's able to be in charge. So you don't need to replace that as well. And you can just put that IoT device out there and it's going to work. So that's interesting. It's just a matter of time to see if this is actually going to be deployed in real hardware and real life solutions. But again, there's work being done on what they call wireless power. So speaking of IoT, you also see this happening, well, not the power stuff, but you see in a lot of IoT happening within wireless networks as well, so indoor networks. And one of the most common ones that a lot of vendors are looking at and already working with is app hosting on access points, for instance, where you can change an access point into not only a Wi-Fi access device, but a gateway for instance, BLE. So that's happening at the moment. You see some solutions where you can utilize the USB port that are on most access points to, for instance, do electronic shelf labeling, where you don't need another infrastructure next to your Wi-Fi infrastructure for those labeling systems. So there are a lot of developments going on. You also see the development of Wi-Fi tags, BLE tags, BLE devices that can connect to other BLE gateways like cameras and access points, but also digital boards, a lot of stuff going on there. And one of the other things is, and that's something that I was talking about with Wi-Fi 6 as well, and 6E, is the access for Wi-Fi guests. Now, a lot of them are still using portals, which is kind of a nuisance because you always have to accept those terms and conditions. And it's still insecure. It's unencrypted, it's open, anybody can listen in, and that's just not secure. So one of the developments that's been going on for years now is called open roaming. This was a Cisco development. Cisco handed it over at the end to the WPA, so the Wireless Broadband Alliance. They still call it open roaming, and it's an ecosystem for secure authentication and connectivity to your guest network, and it actually works really well. So that's something you could look into as well. From an innovation standpoint, this is something that's out there already. Next to that, two other things. Of course, IEEE doesn't sit still. They're still developing new standards. More are coming up. So this is an ongoing journey, as always. And one that I found very interesting, again, from my astro geekness, is the Starlink development. Now, at first, I was a bit reluctant to it because, well, like I said, I'm also an astrophotographer, so I got a lot of problems with a lot of star trails or satellite trails that these 30,000 or 60,000 satellites from Elon Musk are giving me. However, we've also seen what's happening in Ukraine at the moment, that by giving out the Starlink connection kit, they are able to bypass any internet restrictions that are being imposed upon them by having a clean access to internet through the Starlink system, which is, well, again, that's a really big benefit in the current state of matter. So that's what I want to give to you from a development and innovation standpoint. And Matthias, I don't know if any questions came in that we can address at the moment.
Yeah, we have plenty of questions. Should I just read them out, or will you check the Q&A?
Let me check Q&A. How much time do we have?
We still have like about 7 minutes, so
okay.
Let's get started.
All right. Let me see. Somebody can't hear anything. Well, can't do anything about that. Let me see. Get the recording slides. Any thoughts about Wi-Fi 7? Well, I think I addressed it already verbally. Let me see about a change of latency in network communication between devices for BB and B. Well, yeah, that's so the difference. The question is, what about the change of latency in network communications between BB, BE? So with AC and AX, that needs to be figured out. As simple as that. Well, I think the biggest challenge is going to be roaming between the two different technologies. And especially where, if you look at, for instance, light communication and things like that, if your connection suddenly is going to drop, how fast can you connect to the other network? And that's probably going to give you the most latency. And maybe with regards to the latency of transmitting the data, but you see a lot of applications that can deal with a lot of latency at the moment. So it all depends on your application as well, in my perspective. Let me see, because it jumps back and forth. Where do you see Wi-Fi going in the near future in high density environments, school, universities, 6 or 6E? So whether you're going to see 6E or not, that's a bit of a debate that's going on the internet, to be honest. So 6 gigahertz will be there. It's already here. It basically depends on what kind of school or university you're at. And that all has to do, and you can think about it what you want, it all has to do with your budget, and not so much the budget for your installation, Wi-Fi installation. Of course, that's a big deal as well. But pricing of the installations, the infrastructure itself doesn't change that much when you go to a 6 gigahertz solution. But the clients are mostly the higher end clients that will first start to support newer technologies like 11AX, like 6 gigahertz. So if you're at, let's say, a middle school, you're probably not going to see that many 6 gigahertz clients compared to when you're, for instance, a high-end university. So that's probably one of the biggest factors of seeing 6 gigahertz. On the other end, if you're a company that has certain requirements that you put out there for connectivity to your Wi-Fi network, that might be a bigger driver for the adoption of 6 gigahertz. There's also the discussion about, yeah, well, who's going to adopt 6E when Wi-Fi 7 is already being developed? Same discussion. Why not jump into it now? Because Wi-Fi 7 is going to be there, but probably Wi-Fi 8 is going to be a couple of years later as well. So that really isn't a discussion, in my opinion. If you have the opportunity to step into 6 gigahertz now, and if you have the use cases plus the clients, or at least a refresh of your clients, and have one of the requirements to be capable to connect to 6 gigahertz, then yeah, go for it. Go for 6 gigahertz, absolutely. This is the time to do it, because you're going to have a completely clean spectrum to your for your use. So why not? Looking at the time, 3 minutes, I think. What about evergreen products? Yeah, there's somebody who's asked a question. I think it's about more of an environmental question, where you have all these devices on your ceiling constantly being powered up and stuff. I haven't seen any vendor that's really looking into, for instance, lowering the power during certain hours. There are some vendors that can have time schedules where you can shut down a port within specific times. And that again depends on your environment. So if you're in a hospital, it's probably not a good idea to shut down your Wi-Fi network in the night. But in a school, yeah, why not? I mean, it's saving a lot of power. However, you're going to see the requirement for at least 802.3 AT, so PoE plus, to boot a Wi-Fi 6E access point, and probably to have it fully featured, which is most likely using like USB power and all that stuff. It's going to need ultra PoE, so the 60 watts version of PoE. But again, it depends on your vertical. Can you shut down your ports or your access points or radios or whatever? We did some testing by shutting down radios on an access point. That doesn't do a whole lot to your power consumption or on an access point. Let's see, some other questions about compatibility, legacy devices, and other standards. I think I've addressed that verbally. ISPs using Wi-Fi 6 and 7 in relation against 5G. I'll also mention that at the last point as well. Presentation available afterwards. Yes, presentation will be shared afterwards, and it's going to have some links and sources, references in there as well for you to read up. I'll wait for Wi-Fi 9. Yeah, let's see what that does. So I think that's it for now, unless I missed a few, but
Yeah, we have one more question that came through the chat from Adrian. And is there a requirement in the Android version of the smartphone in order to use WPA3?
Yes, there is, but I think the Android versions, even from a year ago, are already supporting it. So if you don't upgrade your phone, then you're probably going to need to. But yeah, there is a requirement, as well as there is for Apple, and for instance, the most common one is Microsoft, of course. You need preferably Windows 11 to go for Wi-Fi 6E first of all, and for Windows 10 for WPA3, but better go a bit higher and look at your drivers, because that's something that's just general for any new standard. Look at your drivers, look what's supporting for your adapter, because not every adapter supports WPA3 too. So you need to look into that as well. But yeah, Android does not need an upgrade. Most devices do support it nowadays. Well, thanks for your attention, and glad you could make it. You will see the presentation ASAP. So thanks again.